All right, so I had a couple requests for more help on experiment 16 busy work. It's very important because it's about half of your week 10 chapter 8 homework as well. Our big worry on this chapter is, in a double replacement, can you find the spectator? Can you find the precipitate? All the answers are here. But much like a fork, if you don't know which part does the stabbing, a fork is a useless tool. So in order to make this table a useful tool, we're going to have to teach you how to recognize things in that yellow category from things that aren't. So this table works perfectly as an X. In that kind of situation, you are spectator, soluble, and you're never going to precipitate. That's also true down here. If you draw an X in the opposite direction, so this opposite diagonal, those would be insoluble, never spectate, but always precipitate. So you're either in this diagonal or that diagonal. That's all we have to watch out for. And unfortunately, the only way to get good at it is to practice. So we'll do a few more practice problems in this lab. So as we do this, just remember a lot of those answers were on the bottles from the lab itself. So I think we did number 1 together before. So let's do number 2. This is lead 2. So lead with a +2, nitrate with a -1, across the 1, across the 2. We have potassium. +1. We have dichromate, which is Cr2O7, -2, so cross that 2 over, that 1 over. Lead and potassium are positive, so switch them. You get potassium with nitrate, +1, -1, those cancel. Just like these cancel when they cross, and those cancel when they cross. What's left over is lead, which is a +2, and dichromate, which is a -2. That's also a perfect match. First thing I would do is balance it. Recognize that there's 2 potassiums and 2 nitrates, so we're going to need 2 potassium nitrates. So it is a balanced equation now. We just need to look at solubility rules. But I'll remind you over and over and over and over again is look for the ones in yellow. These are the ones that are always spectators, always soluble, and usually always present in the reactants because they're safe. They're safe, meaning you can put them in the water, you know they're going to dissolve because they're always soluble no matter what. So do we have any sodiums or potassiums? We have potassium, so water soluble and water soluble. As soon as we find water soluble over here, because we could care less about these, they haven't been mixed together yet, those are your spectators, K+ and NO3 negative. Notice they were in that list of yellow. Like we said to watch out for every single time we look at a reaction, look for these first because they're the ones that always behave, no exceptions. That means the only one left over is the lead dichromate. That could be our solid. And if we look for dichromates way down here, we see that lead's not an exception. So usually dichromates are precipitates. Only when potassium was around was it not, and that was always the case because they never precipitate ever. So again, that's the process of doing those. Let's try another one. Let's try this one up here. So again, this was our solid, we circled it. Let's try this one here with barium. So barium is a +2, chloride is a -1, so cross the 2, cross the 1. We have potassium, which is a +1. We have chromate, which is a -2. Cross the 2, cross the 1. Barium and potassium are positive, so switch. We get a potassium and a chloride, which is +1, -1, perfect match. And then a barium and a chromate, which is a +2, -2, perfect match. But again, notice we have 2 chlorines, 2 potassiums, so we're going to need a 2 here in order to balance it. Much like before, up here we had potassium, I forgot to write it, but nitrate also, one of those ones in yellow. Do we see any of those again? Do we see sodium, potassium, nitrate, acetate, or ammonium? Because they're in almost every reaction. We do see potassium. So as soon as we see that, we know this is water soluble because of it. We know it's going to stay water soluble because they always are, and that tells us the spectator ions almost every single time. Almost every single answer down here will be a potassium, a sodium, an ammonium, a nitrate, or an acetate because those are so well behaved that they're not going to precipitate ever. So as we look at the rest, we're going to say, well, chlorides, they have a category that's important. Chlorides are usually spectators, except for lead, silver, and mercury, so let's watch out for those. We have potassium, so definitely not lead, silver, or mercury. We have barium, not lead, silver, or mercury, so that would be water soluble, and it needs to be. Just remember, these are never answers in the homework or the lab. They either stay separated as a spectator because they're still water soluble, or they're a precipitate. So if in lab we saw a color, we need to know who's that color. Chromates are down here. They're almost always precipitates, except for with potassium. Well, no duh, because nothing potassium is ever precipitating or ever going to be water insoluble. So again, here we have our solid. Try a few more. Aluminum sulfate, we have aluminum with a +3, sulfate with a -2, across the 2, across the 3. We have a barium, which is a +2, a nitrate, which is a -1, across the 1, across the 2. We need to switch the positives. So we're going to get, it doesn't really matter who we do first, we get aluminum with a nitrate. So again, a +3, -1, across them. And then a barium with sulfate. It's a +2, -2, perfect swap. So here again, we crossed them. So notice, I'm going to start here because it's the biggest and the scariest. We have 2 aluminums, so we're going to need 2 of our aluminums. We get 3 sulfates, 3 of our sulfates. That gives us 3 of our bariums, so 3 of our bariums. And then that gives us 6 nitrates, but we already had 6. 2 times the 3 is 6. So now it's balanced. Just like before, do we have any sodium, potassium, do we have any nitrates, acetates, or ammoniums? And we do have a nitrate. As soon as we find those in yellow, we know the answer, because those are going to be the ones that never, ever, ever make precipitates ever. So the ones in yellows are your friends. There's only 5 to remember. You don't even have to look at the chart. Let's prove that the other ones are. So we have sulfates. It says for sulfates, most sulfates are water soluble and spectators. That's true except for lead, calcium, barium, and strontium. Guess who we have? We have one of those exceptions. There's our solid. Aluminum was not an exception. It's still water soluble and it would need to be in order to be mixed together. So never choose these, always choose these. You really have a 50-50 shot, but almost always these are in yellow and these are not. Let's try another one. I'm going to try this one down here for a specific reason that we're about to find out. Potassium is a K+, bromide is a -1, perfect match. Ammonium and chloride, so +1, -1, perfect match. And switch, potassium and ammonium, so we get potassium and chloride, and ammonium and bromide. So everybody here is a +1, -1, so everybody's perfectly matched, so it's already balanced 1 to 1 to 1 to 1. What we need to worry about now is, do we have any of those in yellow? Do we have potassiums? Yes. Aqueous and aqueous. Do we have any sodiums? No. Do we have any nitrates? No. Do we have any acetates? No. Do we have any ammoniums? Yes. And yes. So here, everybody's a spectator, and that's okay. In the lab that we did over this, it should have stayed clear, and this is why. Let's try maybe one more, give you an idea how things are working. The toughest one's probably this one, balancing-wise, so let's do that one. Iron is a 3, because it says so. We have chloride, which is a -1, so cross the 3, cross the 1. We get barium with hydroxide, so that's a +2. Hydroxide is a -1, so cross the 2. Switch the positives. So we get barium with chlorine, +2, -1, so cross the 2. We get iron with hydroxide, +3, -1, cross the 1, cross the 3. So they do have different charges, so they will need balanced. So notice the chlorines are giving it away. What does 3 and 2 have in common? Hopefully you know that that is 6. So if you take a 2 here, that'll give you 6 chlorines. Put a 2 here, that'll give you 6 hydroxides. So when we come back with a 3, that'll give us the 6 hydroxides and the 6 chlorides. So it's really that bouncing back and forth process, recognizing that pattern to be able to survive these kinds of problems. We saw earlier with chlorides, to be an exception of chlorides, you needed lead, silver, and mercury, otherwise water soluble, otherwise spectator ion. So let's look for that. Definitely not silver, lead, or mercury there, so water soluble, and definitely not silver, lead, or mercury here, that's water soluble. So this time it wasn't in yellow, a little bit tougher, but still was not an exception to the halogens, lead, silver, or mercury. Finally, we have is hydroxides, that's at the bottom of our table. Hydroxides say that usually you're going to precipitate. The only time that you're not going to precipitate is when you're in yellow, and that's a no-duh. But also calcium and barium. Let's see if we have any of those. We do have barium, which is water soluble, but again, these don't really matter for the homework or for the lab. What matters is when you mix them together, these separate, and because we're not in yellow or calcium or barium, here's our solid. And that's the one we circle, and that's the color that we're going to see in that lab. Let's do one more, but from the acid-base chapter. Saw several of these in the homework. Now we see them in the lab as well. Probably the one of the tougher ones might be the one at the bottom because it's got a bigger acid. They're all about the same difficulty otherwise. Phosphoric acid is H plus and PO4 -3, so across the 3, across the 1. Potassium hydroxide is a K plus 1 and a hydroxide -1, so that's a perfect match. Switch the positives, we get K plus and phosphate -3, across the 3, across the 1. We also have H and OH, which is just a fancy name for water. So I like to draw them this way just to show you that here's the acid, here's the base, here's the acid, here's the base. Notice we have 3 acids, so we're going to need 3 acids. That's going to require 3 bases to neutralize. That'll require 3 of our bases to neutralize, but notice we already had 3 potassiums waiting with phosphate as a product. Same idea. Do we have anybody in yellow? Do we have any sodiums, potassiums? Yes. Yes. Answer already. So those yellows tell you so much if you just want to look for them. And then lastly, waters are liquid. Can we predict that phosphate is going to be water soluble? Probably not easily, but it is a group 1 kind of metal, and it is an acid. For that reason, they're water soluble. So it's obvious nevertheless. We see it in lab as a clear solution. I can help recognize that one in particular. But this page is going to work just like the others. So hopefully that helps. Went through it a little fast, but a lot of it is translating first, balancing second, and then using that solubility table third to see who's in yellow and who's not. So hopefully that gives you a little bit more practice and a few more answers to finish up our experiment 16.